Hi, I'm Mark Olson. I'm a principal software engineer with Amazon, and I've been focused on storage and virtualization for the last 9.5 years in EBS. Today we're going to talk a bit about the infrastructure that we've built for EBS. Now I'll go through some definitions to ensure that we're all on the same page. This is going to be a technical talk, so we want to make sure that we start with an understanding. We'll talk through the evolution of EBS, and then we'll spend a little bit of time with EBS Block Express and what's next after that. So what is EBS? EBS uses the same interface as a hard drive, but it's important to remember that EBS is not just a bunch of disks. When you provision an EBS volume, we don't take a disk off the shelf, put your name on it, and set it aside just for your use. EBS is really a large distributed system that provides network block storage as a service for EC2 instances. We have data services features such as snapshot, restore, and fast restore, encryption, and modify volume support. And when I say that we're a large distributed system, really EBS is a distributed system of distributed systems. And so there are a number of components that make up EBS, and each one of those is its own little distributed system. Now to give you an idea of how large it's large, on Prime Day this past year, Amazon provisioned 241 petabytes of storage just to support Prime Day. And that 241 petabytes handled 6.2 trillion I/O requests per day and transferred 563 petabytes of data a day. So we read that storage more than twice a day. When we think about distributed systems, and especially one like EBS, we really think about them in two parts. First, we have the data plane. And what we consider the data plane is your compute instance, which has some amount of storage attached to it. That compute instance is running on EC2 hardware that has a Nitro controller in it. That Nitro controller takes your block storage, converts it into network traffic, sends it across the network to the back-end EBS storage servers. Those storage servers are then responsible for persisting that data onto media. All the components that I just talked about, those that touch your data, are what we consider the data plane. The other part of EBS is the control plane. The control plane is really a number of services today, but it makes up or presents the API front ends. And so these are the things that allow you to create, attach, modify, delete your EBS volumes. There's backends, there's storage, there's databases behind it for volume metadata. That's things like who the owner of the volume is, what the performance characteristics are. We have data placement services that make up part of the control plane so that we can ensure that your data is placed for an optimal experience, whether that's near your instance with the right performance characteristics and the right durability characteristics. And while we don't like to see failure, we do know that failure happens, especially at our scale, all the time. And so we also have repair workflows that ensure that your volume remains at the durability level that we've provisioned. EBS was launched in August of 2008. And in the beginning, we launched with a zonal architecture. And so what we mean by that is all of your volumes are contained within the failure domain of an availability zone. And so each availability zone that we launched with has storage servers on it. Those storage servers talk to other storage servers within that same availability zone. They don't talk to other storage servers in other availability zones in the region or even across regions. For availability purposes, we had a highly replicated control plane with data storage in all availability zones. Now this control plane, which we called Storage Manager, was a single service that presented all of the front-end APIs. And it was also backed by a database. Now as we grew, we added storage servers to ensure that we had enough capacity and performance for our customer volumes. The underlying database of our Storage Manager was also scaled to larger and larger hardware. We built read replicas to improve performance, but ultimately, Storage Manager was just a single system. Our goal in building Storage Manager was to be more available by replicating data to other availability zones. Unfortunately, what we didn't recognize at the time and wanted to focus more on, we had a few outages that the blast radius of these outages were much larger than we were happy with. And so what do we mean by blast radius? Availability is very important to AWS customers, and it's part of how we design and build. When we think about availability, we're focused not only on making those interruptions infrequent and short, but also on limiting the impact and the duration of those interruptions to as small a set of customers and volumes as possible. We call this idea blast radius reduction. And so as we explored our architecture, we recognized that the availability of existing volumes was important. We took the first step towards a smaller blast radius by creating a new service called the Configuration Manager. The Configuration Manager stores the map of volume to host, and it is critical to how EBS volumes are managed. When we created this service, we focused on reducing the number of dependencies and interactions. The Configuration Manager plays a key role in the attachment and detachment of volumes from your EC2 instance, but also in the repair of EBS volumes. Because of this critical part, we knew that we needed a highly durable and highly available service. So we built this Configuration Manager based on Paxos-based replication with as few dependencies as possible. And then each one of these is wholly contained within a single availability zone. And so we have a different Configuration Manager in each availability zone. To show you a little bit more about how this participates in our repair process, let's walk through what happens when a server fails. And so in this diagram, I've got a simplified view of EBS with just 5 servers and a few number of volumes. These volumes are made up of one component and they have exactly one replica. This is a very simplified view of how we build EBS volumes today. You'll notice that the servers themselves have different volumes, and they aren't tied to any other server, and they aren't directly peered with any other server. And that'll be critical to understand in a minute. And so if we have a server that fails, our Configuration Manager notices that it fails and takes it out of service. We immediately mark those volumes as repaired or in need of repair. The Configuration Manager will then take those 3 volumes that were impacted by this single failure and find new servers to host the other replica on. And now I mentioned before that we're not tied directly to server pairs. And the reason for that is simple. If I had 2 servers that had 3 volumes each on them, or 3 replicas each on them, and one of those failed, I have 1 server remaining to repair all 3 of those replicas. If instead I have a full mesh, those volume replicas actually can take advantage of 3 different servers, 1 for each server to repair. And so time to repair is better because of the parallelism, and we can take better advantage of the resources available to us. And so we've placed the new replica, and eventually they're fully up to date, and then we can move on. We'll add more capacity into our fleet to replace it, and we'll also be able to rebalance for performance and storage reasons. So we were happy with the improved scaling and blast radius reduction properties of moving the control manager to be an availability zone service. We decided that at this point we needed to focus on the rest of the control plane. Now we could have taken the storage manager as it was. We broke out the configuration manager, which was one of the most critical pieces, and we could have stamped out mini storage managers in each availability zone. But instead what we decided to do was take a step back and think about how we could re-architect that control plane. Storage manager, even though the configuration manager wasn't part of it, still had a number of functions associated with it. And we focused on building a services-oriented architecture that where each service actually had its own, or each function actually had its own service around it. And so this is where the distributed system of distributed systems comes into play. Now, as we've grown and grown and grown, AWS availability zones have grown to be tens of data centers. And as we scaled, even a configuration manager for an availability zone was too big. So we set out to create even smaller boundaries. We asked, what's the smallest blast radius that we could have? And in asking this question, we made a key observation. Instead of a typical database where every client of the database needs access to all the data, we recognized in the case of the configuration manager, each client only needs a small and specific amount of information. In fact, the clients of the configuration manager are the storage servers and the EC2 instance, and they only care about the volume that they're trying to attach or trying to get information on or trying to repair. And so we broke this down into even a smaller cell, and this led us to constrain the blast radius even further. we found that we could build a database for each individual volume. And this led to Physalia and millions of tiny databases. The only clients required at this point, like I said, are the storage servers and the volume itself. But there was a challenge here. Instead of tens of databases, we now had millions of databases. And so how do you design a system that can scale and maintain and manage millions of these little databases? Even though the blast radius of each database was smaller, it was a more difficult management problem. And with this, we had to build automation into the design. So this wasn't typically how you would scale. You might add automation on as you scale beyond tens or 50. With Physalia, we built automation into the initial design. We were also happy with Paxos as our backend, as our storage. And so Physalia cells are built on a seven node Paxos cluster. You can read more about it at the white paper we published about Physalia. One of the other things that we think about as we're scaling our control plane and as we're building out and operating our control plane is static stability. And static stability as it relates to systems is the ability for them to return to a steady state after small disturbances. And so what does this mean for EBS? What this means is when we have a network event or maybe a power event or some reason why your EC2 instance can no longer talk to the EBS storage servers, we want to be able to repair that connection and bring back availability to your EBS volume as quickly as possible with as few dependencies. In EBS, our goal is to not involve any control plane services to restore that connection. Now let's focus a bit on the data plane. Even when EBS first launched, a volume was not just a disk. It had features that allowed us to move your data around to different storage servers in support of maintenance and upgrades and things like that. But we did have limitations. A volume is only hosted by a single pair of servers, and therefore constrained by the resources available on that single pair of servers. To bring higher performance or higher size, higher amount of storage than a single server could achieve, we began sharding volumes across many servers. Now with this, we were no longer constrained by individual storage nodes, and we were able to change the replication properties of that volume depending on the performance requirements of the individual shards. Smaller objects are also easier to increase the utilization of our storage servers. Now, when we have more shards, we have to worry about the durability of each individual shard. And so the durability of your volume is the combination of the durability of each one of those shards. But since the shards are smaller, there's less data to replicate, and so they're faster to replicate in failure. And so by doing this, we were able to improve the durability of your volumes. Now, we went through a huge internal migration where we converted all the volumes to this, and then recognized that that would be a great feature to give to our customers. And so the tooling that we built actually became modified volume that gives you the ability to change the performance characteristics or even the volume type of your EBS volumes while they're online, while they're attached, without any downtime. Moving out from the storage servers, we started to focus on our network protocol. As we sharded volumes, we were recognizing that we had less throughput than we expected to get back to our instance. And what we realized is that by having many storage servers sending data back to your instance, we overflowed the funnel. So if you can think about the network to your instance as a funnel, and you've got a bunch of water that's going into that funnel, when you're out of space in that funnel, it overflows and it spills out. Well, the same thing was happening here. When we built EBS, we built on top of a general purpose network stack. And that network stack has to handle all sorts of failures. And one of the things that it does when it gets a lot of packet loss or data loss, things spilling out of that funnel, is that it backs off. And so instead of getting the amount of throughput that's available in that funnel, we actually weren't able to fill the funnel. We were only able to fill about half of the funnel before we started having problems. And this is because that network stack would back way off, have to retransmit the data that spilled over, and back off even further and contend with itself. The other problem with our general purpose network stack is that it turned out to be more difficult to offload in hardware than we desired. So when we built EBS, we weren't expecting to offload into hardware back in 2008. And so that was something new that we had to contend with. We've also evolved our network infrastructure in our data centers. Our networks today use something called equal cost multipathing. And what that means is between two endpoints, there are actually multiple paths that your data can take. The network stack that we were using was not able to take advantage of those multiple paths. So we had to wait in the event of a link failure somewhere in the core of the network. We had to wait for the network to route around itself, as opposed to being able to respond quickly. Now, this is still fast in the low order of seconds, hundreds of milliseconds to seconds, but it's longer than an I/O should take. So by looking at our data center and recognizing the properties of our data stream, we're able to go through and redesign our network protocol. Now, we worked with our infrastructure partners and built a new purpose-built protocol called SRD. Now, SRD is the underpinning also of EFA, the Elastic Fabric Adapter, but we've been using it in EBS for some time now. It's designed to route easily around the failures that we see in our network and built with our data center in mind. And so I spoke a bit about hardware offload, and this is where the Nitro card for EBS comes in. The Nitro card for EBS is something that we've been using since we introduced the C4 instance family. It presents an NVMe controller and includes offload support for hardware-based encryption and our storage protocol. It also gives us the opportunity to give EBS optimized by default with its additional network. Now, if you've been paying attention to the instances that we've launched over the years, it wasn't until C5 or the Nitro system that we actually presented NVMe. What we did with C4 is we actually presented the NVMe device into the Xen DOM0. So C4 uses the Xen hypervisor, which has a driver domain. And in that DOM0, we presented NVMe. In 2015, the driver space for NVMe was not mature enough, and so we felt that that was the safest and best experience for our customers. We still relied on the Xen split device model to support this storage into your instance. Now, we've been working on the Nitro card itself, and with our latest generation of Nitro card, we were able to greatly improve the performance of R5 instances. And so we recently launched the R5B instance type, which is a EBS optimized, performance optimized instance. Now, we took the R5 because most of the customers that are running our R5 are running database-like workloads and other workloads that can take advantage of higher storage capabilities. With R5B, we can go to almost 4 times the performance, so up to 260,000 IOPS and up to 60 gigabits of EBS optimized bandwidth. This is built entirely on the Nitro and SRD stacks with the newest, latest generation Nitro controller. So we moved to a services-based control plane in our architecture in our control plane, and it improved our agility and our ability to reason about the control plane. We asked ourselves, can we do the same for a high-performance data plane? And so there's some obvious benefits around agility, but there's some obvious challenges as well. In a data plane, you can't use a REST API to coordinate between services. You're going to need to have better defined APIs, but you're going to have to use internal memory structures, which are often harder to change after you've built them. But there are some benefits as well. By reducing code in the fast path, it allows us to improve the performance. And so we pulled a few services out of the data plane, a few of the data services out of the data plane initially, and had some great results. Again, in a very iterative fashion, we did 1 or 2 at a time, and as that improved, the performance of the code improved significantly. But not just the performance consistency also improved. The other thing that's been valuable for us is that the smaller code and the smaller components are much easier to reason about, not just in security and correctness, but also the performance characteristics of that code. Now, putting this all together, the disaggregated data plane the disaggregated control plane, we split all the data services out. That brings us to EBS Block Express. And so EBS Block Express takes advantage of this disaggregated infrastructure data plane, builds on top of that with Nitro and SRD to provide a significantly more consistent I/O latency profile, and really the first cloud SAN that's available. To give you an idea of what Block Express is capable of, we're announcing a preview of IO2 Block Express. With IO2 Block Express, you can now have the performance of a SAN in a high durability block store in the cloud with all the benefits of the cloud, including the ability to scale, provision, and pay for just the capacity you need. Now, IO2 Block Express volumes have the same IO2 durability of 5 nines, but they have 4 times the performance, 256,000 IOPS and 4,000 megabytes per second. The other neat thing about IO2 Block Express is they have sub-millisecond average latencies and 4 times the capacity, so you can provision up to 64 terabytes at that same 5 nines durability with that same sub-millisecond latency. Let's take a look at how that latency compares to IO1. So this is a probability distribution graph. On the left-hand side of the graph is the minimum latency that you'll achieve, and on the right-hand side is close to the max. It's not quite the max. Now this graph is sampled over 1 million data points of a 16 kilobyte write workload. And so IO1 and IO2 were configured similarly. They were both attached to an R5B instance. And so the differences that you see here are differences in the infrastructure. IO1 volumes, you can see, start out with a little bit higher latency, but the curve slopes up, and then the tail latencies start to take effect on the right-hand side. With IO2 Block Express, we were both able to reduce the latency, change that slope of the bulk of that line to more horizontal, and then that long tail latency, we shifted way to the right and reduced the magnitude of it. So this shows the performance consistency and the higher performance that you're able to achieve with IO2 Block Express. So the question I've gotten so far is what applications will work with IO2 Block Express? And the answer is all of them will work, including those SAN workloads that you've got on premise today. It's really best for applications requiring low latency I/O or the higher performance and higher durability characteristics that our infrastructure can provide. Now, while these volumes are in preview, there are some limitations. IO2 Block Express volumes today support encryption and support snapshots. They don't currently support EBS encryption by default. Can only use them with the R5B instance family. And some of the features like modifying volume and multi-attach are also not quite available yet. But we expect to get these in the coming months. So what's next? So with Block Express, we're looking to add all EBS features. We want to ensure that we have support for all Nitro instances. But really, we're asking for feedback from you. What would you like us to work on next? And with that, I hope you enjoyed the talk.